Hi everyone. In this video, we are going to start section 2.1, the first section of chapter 2. Chapter 2 is titled Limits. I don't have it on the slide here. But 2.1, we're just going to get into a preview of calculus. It's kind of an overview of the two overarching topics that we will encounter as we move through the semester. And the first being what's called differential calculus. Okay, so calculus was, when it was first developed, Isaac Newton and another mathematician named Leibniz, they were working at it at similar times, but from two different directions, which is kind of cool. So the same calculus that we do today was studied by these two guys, and they were kind of, I don't know if they were actually racing, but they were working their different branches, and ultimately put out these different texts on calculus, and that's the same thing or similar to what we study today. All right, the first one, differential calculus, deals with, well, slopes, something that you've seen before. But the topic of slope as it relates to this line and as it relates to this parabola is very different, right? Because we know the slope of this line, if I'm giving you its equation, is f of x equals negative 2x plus 3. We know that its slope is constant. Its slope is negative 2 the whole way, right? But on our parabola over there on the right, well, its slope isn't constant. It changes, right? Over here on this section of the graph, right over here, right? The slope, if I were to like touch the graph, it would be, I kind of came close there, it would be negative, right? As I get closer to the origin, it levels out a little bit, right? Right at the origin, I've got a slope right there of what appears to be 0. Right here, we've got a slope. Here, we've got a little bit of a steeper slope. So on my parabola, the slope is, well, it's changing, right? On any curve, we can look at the slope at a point, but how do we actually compute that? And how is it possible to compute that with certainty? All right, and it boils down to first understanding the slope formula that you've used likely since 8th, 9th, 10th grade. The same formula is how we first begin to understand calculus. Okay, so the first step is to compute the slope of a secant line. A secant line is a line, so this is the orange line in my picture, that passes through my curve and hits it twice. Later we'll talk about tangent lines that pass through a curve and hit it just once and only once. But my secant line hits the curve twice. Okay, if I have 2 points, I can compute the slope of that line. So this is the slope of the orangey yellowy line, and we're using that to approximate the slope at this point a comma f of a. All right, so we have our slope formula, y2 minus y1 over x2 minus x1, just written a little bit more fancy. And I've got the notation down here at the bottom, the slope of a secant line, m with a subscript secant, f of x minus f of a over x minus a. All right, but if my goal is to approximate the slope right here, well, this would be a pretty decent approximation, right? But it doesn't look quite as steep as the slope at a, right? So what we can do is, instead of this point x comma f of x right there, well, let's get a little bit closer, right? Now, if I draw a green tangent line that looks decent, okay, this would be, the green tangent line would be a better approximation of the slope at a. So this new point would be maybe x1 comma f of x1, because it's a different point. And I can compute the slope using the same exact formula. How do I get an even better approximation than that green line? Well, we take a point even closer to the blue point, the a comma f of a, and draw that tangent line. And that drawing wasn't very good, but hopefully you get the concept of what I'm talking about here. We're moving closer and closer to the point A, thereby getting better and better approximations for the slope at that exact point. Okay, always using the slope formula that you've seen in the past. Let's look now at an example as I scroll down a little bit here. Maybe we'll zoom in a little bit more. There we go. And the example says, estimate the slope of the tangent line, or rate of change, to f of x equals x squared at x equals 1 by finding slopes of secant lines through 1, 1, right? So at x equals 1, right, if you plug that into the graph, you get 1 comma 1. If you plug that into the function, excuse me, you get 1 comma 1. and each of the following points. So part A gives us the coordinate 2 comma 4, and part B gives us a fraction-y coordinate, which we'll deal with 3/2 comma 9/4. Okay, so for both of them, we're going to find the slope of a secant line. Okay, so my y2 in both A and B is going to be the given point. So we're going to go for the y2 minus y1, 4 minus 1 over 2 minus 1. Right, let me actually write, so I know I already did the work, but let me write the coordinates that we're using for part A, 1 comma 1 and 2 comma 4. So the y2 minus y1 is 4 minus 1. The x2 minus x1 is 2 minus 1. Numerator we get 3, denominator we get 1, so the slope is 3. All right, that's pretty decent, but that doesn't tell me the slope at 1, 1. Is it steeper than 3? Is it less steep than 3? Well, let's move a little bit closer. 3/2 is a little bit closer to the point 1, 1. So for part B, now we're using 1 comma 1 and 3/2 comma 9/4. So the slope of our secant line for part B is now my y2 minus y1 is 9/4 minus 1 over 3/2, also minus 1. All right, let's do that subtraction. 1.5 minus 1 is 1/2 in the denominator. And let's see, 9/4 is 2 1/4 minus 1 is 1 1/4. So let's say that that is 5/4, excuse me. And when you simplify that, you get, let's see, 2.5, or let's say 5/2, 2.5. All right, so we've gone from a slope of 3 when we were 1 unit away to a slope of 1.5 when now we're only half a unit away from the point. So the next step would be to get even closer if we wanted a more accurate answer. All right, we'd have to move closer. Instead of 1.5, which is 3/2, we'd use like 1.1 or 1.01 to get a more accurate answer. Okay, now instead of just talking about slopes, we can also apply it to a good real-world interpretation of slope and a representation of slope, and that is average and instantaneous velocity. Velocity, think like the speed of a moving vehicle or of a moving object. Okay, and if I have a change in position over a change in time, so I'm thinking my change in position is driving from my house to work, and the change in time is how long that takes, I can compute the average velocity if I know the distance that I traveled, that's the y2 minus y1, and the x2 minus x1 is the time that it took to do that. Okay, so you can read through the definition. This is the same formula as the last slide, just put it in a different context, a context of velocity and a change in position divided by a change in time, but it is still a y2 minus y1 over x2 minus x1. All right, so that's called average velocity. And then the second definition for instantaneous velocity, well, that is the velocity that you are approaching as you get closer and closer to that point t equals a. So if you shrink that distance away that you're moving, that's going to be that gives you the instantaneous velocity. So think looking down at the speedometer of your moving car. That is your instantaneous velocity that you're traveling right now. Now I'll scroll down here and we can look at an example using that concept. So we have an object moves along a coordinate axis so that its position at time t is given by that formula s of t, which I'll write down here. S of t is equal to t to the third power. So we're not talking about like the graph. That represents the position of this object at any time t. And it says estimate its instantaneous velocity at t equals 2 by computing the average velocity over that given interval. And I'm going to do something before I use their interval. All right, so I want the average velocity at t equals 2. All right, so the first step is to figure out where the object is at 2. S of t is 2 cubed, which is equal to 8. All right, and let's see where the object is 1 second later before we actually answer the question that we're asked. What if t equals 3? Well, S of 3, plug 3 into the function. Oops, that should say s of 2 before. My bad. There we go. S of 3 is 3 cubed, or 27. Okay, so now my average velocity, v sub avg, is the y2 minus y1, 27 minus 8, the change in position, not the change in y values really, but it's the change in position, divided by the change in time. 3 minus 2 is 1. 27 minus 8 is 19. Right, so we're not really given units in this one, but that object is traveling at a rate of 19 units per second. So I don't know if it's meters per second or feet per second. We're not given the units, but so we can just. But that's what that 19 represents, the velocity of the object. All right, now when t equals 2 and s of 2 is 8, we're actually going to answer the question now. Now our interval ends at t equals 2.001. So we need to figure out what is that evaluated inside of the function. So if I cube 2.001, what do I get in my calculator? Well, I typed it in and I got 8.012, a couple of zeros, a 6, a couple of zeros, and a 1. So I'll go 8.012 will be accurate enough for this, for my purposes here. And now we need the average velocity, v sub a v g, is equal to, we'll take my 8.012 minus 8 divided by the change in time, 2.001 minus 2. Do my subtraction, 0.001, and it looks like when I type that division into my calculator, I get 12.006. All right, so the speed, the velocity of the object went from 19 units per second to a little bit more than 12 units per second. So if I were estimating the instantaneous velocity, so if I were to pick closer and closer points to 2 seconds instead of 2 and 1,000th, how about 2 and 1,000,000th, right? What are we getting closer and closer to? I think 12 meters or feet, 12 units per second, that might be a good estimate. And we'll learn later in the course how to find the exact value, not the estimate, the exact value. But for now, we're just talking about slopes. All right, now the other branch, the other side that we approach calculus from is called integral calculus. And really the main key question in integral calculus, instead of how do we find the slope at a point, with integral calculus, it's how do we calculate the area underneath a curved region. So in this case, under the shaded region, if I want the area of that stuff, what's the best way to find that exact area? And the way that we do that, the way that we start to investigate that, is to approximate the area. So the same as with the slopes at the beginning, we're approximating the area, and we're going to do our best and easiest approach is to divide this region up into rectangles. Rectangles, those are really easy to get the area of. Area of a rectangle, base times height. Boom, done. Area of a curvy thing, I don't really have a formula for that with this kind of a curve, right? If it's a circle, if it's a triangle, sure. But a random curve, we don't have a million area formulas. We only have a few. So the area of a rectangle, that's what I'm going to base all this off of. So I'm going to start out by dividing my region up into 1, 2, well, no, let me move that second one. 1, 2, 3. So we've got 4 different... we've subdivided it 4 times into 4 separate regions. That's what I'm trying to say there. Sorry about that. And we're going to draw 4 rectangles. So I've got this one, I've got this one, I've got that one, and then I've got that one. There we go. Okay, so I've got 4 rectangles, and that's going to do a pretty decent approximation, right? This area of that rectangle is a little bit below, a little bit under the actual area of the region. This rectangle here, a little bit under the actual area of the region. This one here, still a little bit under. So we're underestimating the area of our region. And this last one here, this one ends up going a little bit over. Let me draw that line all the way down like that. All right, so it's a decent estimate. All right, and it's the first step in understanding integral calculus is to compute the area using rectangles. Now, I drew them that way. I could also, or I drew them from the left endpoint of the rectangle. I could also have done something different. So let me erase this. Erase, erase, erase. I'll draw my region, or my subdivisions again. 1, 2, 3. That looks about equal. There we go, like that. Okay. I could also have gone from the right endpoint. The right endpoint. And there's my first rectangle. There is, oops, that went down. Try that again. There is my second rectangle. There is my third rectangle. And that one is my fourth rectangle. And you see in this case, it looks like we're going to get a little bit of an overestimation because we have those two sections kind of sticking out, but only have one that's underneath. Okay, and again, each of those rectangles, super easy to compute the area of length times width, length times width all day. Okay, so that's the first step in the process of understanding what we will encounter later in the semester called integral calculus. Now we'll do one example where we have the function f of x equals x squared plus 1, and the interval is from 0 to 3, and we can see in the picture that we have this divided into 3 different rectangles. We can also see in the picture that it looks like we're going to be underestimating the area of this region, right? So whatever our answer is, it's an approximation, but it's certainly less than what it actually is. All right, but we can still do the problem. There's still value in finding some areas because this is going to be an important step in understanding later on in the semester what is going on in integral calculus. So what we'll do is it looks like this first rectangle, right? It looks like its height is defined by the left endpoint. Okay, so if you weren't sure what I meant there, take this second rectangle. It looks like its height is defined by the left endpoint, and the third rectangle appears to have its height defined by the left endpoint. Okay, if we were using right endpoints, then we would have this red point up there, this red point here, and this red point here, and our 3 rectangles would be an over approximation for the region. Okay, but we're using, it looks like this one, this picture uses left endpoints, right? So my left endpoint, the first rectangle, f of 0, 0 squared plus 1 is 1. For the second rectangle, f of 1, the left endpoint, 1 squared plus 1 is 2. And the third rectangle, f of 2, 2 squared plus 1 is 5. So why did I need those 3 numbers? Well, for each of the 3 rectangles, I need a base times a height, right? So if I'm just going to label it like this, rectangle 1, his base, let me write equals, base times height, the base is 1, and the height is 1, so the area is 1. This is the area. All right. For the second rectangle, rectangle 2, base times height, the base is 1, the height is 2. 1 times 2 is 2. Okay, so where am I getting this from, right? The base here, 1. The base here, 1. The base here, the width of each of those 3 rectangles is 1. The height of the first one is 1. The height of the second one is 2. The height of the third one is 5. And you can count it right there on the picture if you want to. Rectangle 3, we'll do this last one. Rectangle 3, base times height is 1 times 5, which is 5. So the total area, total area under the curve, 1 plus 2 plus 5 is equal to 8. 8 square units. Okay? it's an approximation. It's an estimate. It's an underestimate. We can see that from the picture, but it is the first step in understanding this process. If I wanted a more accurate answer, well, instead of 3 rectangles, what could I do? How about 6 rectangles? Instead of 6 rectangles, if I want an even more accurate answer, how about 12 rectangles, right? The width of them would be a little bit more complicated. The heights of them would all be decimals, so that'd be annoying, but it's going to give me a better answer. And if you want the best answer, stay tuned. Later on in the semester, we will dive much deeper into integral calculus and get the exact area underneath that curve. That's the end of today's video. Thank you very much for listening. Hopefully now you've got enough of an understanding to attack the homework. Please let me know if you do have questions, if you run into things that I haven't addressed in this video. Let me know, and I will do my best to help you out to answer those homework problems. Again, thank you very much for listening. Have a wonderful day.